Thank you very much, Igor. The fact that I'm wearing a tie does not reflect any lack of respect for the audience. So let me immediately press on. The title here you'll see is different from what it is on the agenda. I think I was in hospital when Igor dreamed up the titles of the talks, and so he just pulled something out of the air which he thought would work, but I want to be much more modest about my presentation. I'm not going to present any radically different theories, but rather to embellish on a theory that's been around for quite a while. Joe Wang and Joe Lemberg are the students who are working with me. They're, of course, the people who are really doing the work, and I should thank them, and I should also thank, of course, the California Energy Commission for the support they provided. So there are three schools of thought here regarding how water trees grow. There's an electromechanical theory which says that the electrical field causes mechanical stresses which are sufficient to damage the polyethylene. And there's some evidence of that, e.g. the effects of frequency on tree growth. I'll show you a slide on that in a moment. But it's a laboratory study, so it doesn't mean as much as it would if we could somehow do experiments lasting over 20 or 30 years, which of course we can't. Then there's a chemical school of thought, which you heard Steve expound on this morning, which says that there are environmental effects which, coupled with the electric field, cause chemical, or if you prefer, electrochemical deterioration. And the evidence of that is, for example, the interior surfaces of water trees are oxidized. And the tree growth is generally accelerated by ionic impurities. So there's some evidence that that's what's causing water trees to occur. Now, the truth, as Steve pointed out this morning, is probably a combination of both effects. And there is this model by Zeller showing the consequences of ionic species on these electromechanical forces, and also on the chemical potential, I might add, the propensity for the species to react. And alternatively, we can think in terms of the propagation of a mechanical tree proceeding if the bonds in the polymer are weakened by chemical attack. So what I want to talk about is well, there's the evidence that there's a mechanical phenomenon that's involved, because in a laboratory experiment by Yoshimura, it's clearly demonstrated that if you apply an AC for a certain period of time, then the growth of the water tree is greater at higher frequency. But do note that it's not proportional to that frequency. So how do I work the pointer on this? Anybody know? That one. Okay. So if I take this number and compare it to that number there, it's not the ratio. The ratio of these ordinates is not the ratio of the frequencies there. So it's not quite as simple as that. So let's come on to the ideas what I want to present here. It's straightforward to calculate the fields and forces around idealized voids. Steve does it both analytically and numerically. We tend to do it numerically. These forces are weak, except where the geometry distorts the field. From these forces, we can calculate the stresses acting on the cross-linked polyethylene. We've done mechanical testing of the polyethylene in air, and so have other people. And that shows that the polyethylene is unlikely to fail under a static load of a few megapascals, similar to those produced by mechanical forces. So at first glance, when you do the experiment of putting the material under stress, you reach the conclusion that this school of thought, which says it's an electromechanical phenomenon, that school of thought you're inclined to dismiss. However, we should think about fatigue loading. Because under fatigue loading, a few megapascals is sufficient for the cross-linked polyethylene to fail over the long term, even at room temperature and even in the absence of any hostile chemicals. Notice this is sort of not altogether, this means to look like consistency with experimental results, because, of course, if it's DC, then there's no fatigue, right? The force is constant. So it's under AC that we have the possible occurrence of fatigue. So we'll finish off by speculating, this is speculation, that at higher temperatures or in the presence of aggressive environments, fatigue failure is even more likely to occur in the long term. So some of you in the audience have seen this slide ad nauseam, but there may be a few people out there who haven't been subjected to the horror of it. So let me describe what we've got over here by way of a finite element calculation. So this is a void, an ellipsoidal void. Only one half of it is shown, of course, because it's axisymmetric. And this void has got is sitting in the polyethylene, and it's got properties which are different from the polyethylene. Perhaps it's filled with water. And this void, incidentally, is quite small. It's 100 microns from there to there. So that's the width of a human hair. Or alternatively, this is a region where there are sort of effective properties, so that we might, in fact, think of even smaller voids being located within here, and there's some sort of effective property in here which is different from out here. Most notably, the permittivity here is different from the permittivity out here. So when that occurs, then what happens? It distorts the electric field. So the lines here are isopotential lines. The arrows indicate the magnitude and direction of the electric field, and you can see that in the vicinity of the poles of this ellipsoid, there's a much higher electric field than way out here. There's 1,000 volts between here and here, incidentally, in this calculation. I think it's 1,000 volts. So that results in some forces. There are body forces acting throughout this system, which are given by this equation here. And notice it's the square of the gradient of the square of the electric field which appears in here. So these forces are very high here and very high here. And out there in the bulk of the polyethylene, of course, they're essentially negligible. So we compute those forces, and then we feed them into another finite element program which determines the stresses that are acting in the system based on that distribution of body forces. We also include some stresses due to surface charges. So there may be surface charges at this interface between this void region and the polyethylene, and those can be included in the calculations as well. So these are the calculated stresses. I can't remember the details of this particular calculation, but those are ellipsoid, and these are the stresses which are capable of damaging the material, maybe. And you see the magnitude here is quite small. It's only 3.5 kilopascals. So that's a pretty small stress that you might subject a material to. Almost any material in the world will withstand that stress. But if you take that ellipsoid and make it longer, so the aspect ratio becomes 15, 20, so on, then the maximum stress goes up. So now we're talking about, this is 10 megapascals, this is 2 megapascals, this is 4 megapascals. Try and keep in your mind a stress of the order of about 2 or 3 megapascals. And it depends upon whether you include just the dielectrophoretic stress, or whether you include that surface charge effect as well. Either way, we're talking about, for height to width ratios of around 25, something like that, stresses that are 1 or 2 megapascals. Now, Steve Boggs likes to question us at this point by saying that, in fact, if you got those, when you get up to those stress levels, you're at an electric field strength which will cause breakdown of the polyethylene. So we checked that out and took a number from Zeller's 1987 paper, which identified the breakdown field for polyethylene. Zeller, as you probably know by now, is the grand old man of water treeing. Steve Boggs is the grand young man of water treeing. So anyway, you take Zeller's figure here, and that means if you went above this ratio over here someplace, then you would indeed have electrical breakdown, and that exceeds the electric breakdown strength of the polyethylene. So numbers up here are unrealistic. But you can see realistic numbers are, again, in the range of 2.5 megapascals. So that was encouraging, because what can you do with 2.5 megapascals? Well, you can do the following. This is a couple of photographs of the materials we've tested. These are materials taken from a commercial cable. I think it's taken from a general cable sample. So we cut the polyethylene from the cable and mounted in this mechanical testing machine. and stressed these samples in some way. Now, there are various ways of doing this. You can apply a constant force, for example, or you can apply a constant rate of separation of this grip and this grip down here. And I'll call that static testing, for want of a better word. So we would slowly separate these two things and measure the stress which is subjecting, to which we're subjecting the sample, at the same time measuring that separation, so we're measuring the strain. Alternatively, we can take these things, these grips, and oscillate them, right? So we can do that sort of thing, and we can do that sort of thing at about 5 hertz. And this is what you might get out of sampling a few materials in this way. So I think we're losing battery power here. But anyway, if we look over there on the right-hand side, you can see, I'll walk over and point it out. This is a sample before testing. The rest of the samples are after testing. And you can see some of them come apart. Some of them simply stretched so far that they reach the limit of the machine. The machine can't stretch them any further. And if we plot the stress versus the strain, so this is for a constant strain experiment where we're separating, thanks a lot, Steve, where we're separating those grips gradually at a fixed rate, and then the stress increases quite rapidly to start with, up to about 5 megapascals. This is a case of cross-linked polyethylene, and this is tree-resistant cross-linked polyethylene. And I wouldn't claim there's any significant difference between those two. But you can see it takes something of the order of 7, 8, 9, 10 megapascals to actually break this stuff in a static experiment, right, where we're applying a constant strain rate. It takes considerably more, incidentally, if you use high-density polyethylene, but that's irrelevant for the present moment. So these ultimate tensile stresses of these polyethylenes are 11 and 9 megapascals for the cross-linked and the tree-resistant. And so none of these polyethylenes should fail under a static load of 2.4 megapascals, which we calculate from a mathematical model. So it would appear at this point in time that the mechanical model is invalid. However, what we've now got to think about is what happens under a cyclic load. And to start with, we'll take the material through one cycle. So here's taking a material, loading it up to about 9.5 megapascals, and then unloading it. And you could see when it's completely unloaded, it's been strained by about 19%. So this material undergoes plastic deformation when we subject it to these stresses. In fact, it even undergoes plastic deformation when we subject it to a maximum stress of about 2.5 megapascals. Now that's a clue, because if a material undergoes plastic deformation, then in fatigue, it can fail in fatigue. And so what we do next, of course, is the obvious experiment, and do some fatigue experiments. Before I describe those results, well, these are some of the results, in fact. Let me show you how they fail in fatigue. So if we apply, let's see, 3 megapascals here, this is the elongation as a function of the number of cycles. And you can see this is ranging from 20,000 cycles up to 100,000 cycles here. This is at 5 hertz. So this material deformed quite a bit to start with in the first, few hundred cycles perhaps. And then it didn't deform much more until we got up to about something like 90,000 cycles, and whoop, it essentially broke. So you can see that this fatigue failure is well defined. We can identify the number of cycles that it takes to fail this material at 3 megapascals. At 3.25 megapascals, it occurs much earlier. At 3.5, yet earlier, and at 4 megapascals, it occurs like that. I mean, this might appear to be instantaneous, but of course it's actually several tens of cycles, perhaps even several hundreds of cycles. So this material is failing under fatigue at stresses which are starting to approach the region that we calculate from our mathematical model. And we can plot those results, and you plot them on a log-log plot, and it's roughly a straight line. I've chosen to plot it on a linear axes, because it's a bit easier to explain that. You can see there's a curve here which fits the data. That's the equation for the curve, and it fits the data reasonably well. So in our experiments, it takes 10 hours to get to this point here, and it takes 40 minutes at 120 hertz. Why do I care about 120 hertz? Because it's the square of the electric field that counts in terms of what's happening out there in the cable, and that square of that field is going at 120 hertz, not 60 hertz. So what this is saying is that this is the magnitude of the fluctuations in the stress in this cyclic loading and unloading. You can see then that this thing at a stress amplitude of say 3 megapascals will fail at something like 20,000 cycles. Sorry, 200,000 cycles. So what's it going to fail at say 2.5 megapascals? Well, obviously I have to do an extrapolation out here. And I can't do experiments for 20 years. So the extrapolation on this slide is rather wild. But nevertheless, I'll engage in it. I'll take that equation from the previous slide, and I'll figure out how long it takes to fail at, say, 10 to the 10 cycles. And at 120 hertz, that's 2.6 years. And the stress amplitude you need for that is 1.74 megapascals. If it's 10 to the 11 cycles, that's 26 years. This begins to sound like the lifetime of a cable. The stress amplitude is 1.5 megapascals. Let me stress what I mean by this. Dreadful pun. That's actually taking the stress point from 0.15 megapascals to 3.25 megapascals. So that's sufficient to make the stuff fail after about 26 years. And those are then in the range of the stresses that we've calculated. So the failure mechanism isn't the sort of static loading of the polyethylene, but a cyclic loading of the polyethylene that causes it to have stresses which will fail it. Now, you pose the question, I think, is a fatigue phenomenon a real phenomenon, or is it simply the cross-linked polyethylene is simply creeping, which creeping is a slow deformation under load. Well, let me come back to that slide for a moment. I'll ask you to note these predictions are from room temperature measurements, and the question is posed, what happens at higher temperature? But let me deal with that first question before we go on. These are creep curves. So this is the business of taking and applying a constant stress to the sample. This is not fatigue. This is a constant load applied to the sample. And these loads are shown over here on the right-hand side. So at 7.5 megapascals, the stuff undergoes some sort of elastic deformation to start with. And then it slowly gets longer and longer and longer and longer, and suddenly it starts to fail at that point there. And of course, if you go to higher stresses, then the failure occurs much earlier. And this is time in seconds. I think that's 10 to the 6, 10 to the 4 down there. So I can take that data and put it on the same plot as the one I showed you a few moments ago, slightly redrawn. So these are failure under creep. Now I've used this as time, rather than using the cycle number, which I used when I plotted that data. But then take this data, since I know the frequency, and I can plot that in time as well. So this is creep failure, just simply the failure of this material when you apply a load. This is fatigue failure. So you can see this fatigue phenomenon is real. If I was to, for example, apply 7 megapascals, this thing would fail in a few tens or a few hundreds of seconds, whereas if it was simply creep failure, it would last up to something like the order of 130,000 seconds. And you can, if you worry that I'm extrapolating there, you can do that calculation, similar calculation at 8 megapascals. So this is a real phenomenon. This material is failing under fatigue under the conditions of our mechanical testing. Temperature. Okay, so these cables get hot. I think some in the audience might dispute that, but what we did was to go ahead and did a finite element calculation of the temperature distribution in a cable. So heat is being generated in this region here by the current I squared R, the current flowing through the central conductor. And we simply specify the outside temperature here as being room temperature. We said we'll put no current through the concentric neutrals. What sort of temperature distribution might we expect? Well, of course, it gets hottest in the middle. So we're interested in the maximum temperature of the polyethylene. This is the polyethylene layer here. And if I plot that maximum temperature versus the current in the central conductor, you can see that if I go up to 300 amps, then it's starting to get warm. If I go up to 500 amps, it's up to 80 or 90 degrees. So indeed, these cables do get warm. And another piece of evidence is something that Lamar Cunningham at our first Berkeley workshop, which was 2 years ago, reported. I think these are actual measurements of temperature in the cable. These numbers here, this is 96 degrees, 102, 103. And you can see the temperatures become quite high. This is the current passed through this particular cable. So indeed, these cables get hot. And so what we have to address is the question, what happens by way of fatigue behavior when these materials are heated by say, the current through the central conductor? And we don't have any evidence of that. We can't find any evidence of the effect of temperature on the fatigue behavior of polyethylene. But what we can find is the effect of temperature on the fatigue behavior of polystyrene. I don't know why we've had the word twice there, but there you are. So this is 0 degrees, 30 degrees, 45 degrees, 65 degrees, and so on. So you can see, let me pick some particular stress. Let's say 10,000 psi. I'm sorry to use a unit that's different from the one I've been using so far, but anyway. If you take that material, let's do a little bit of extrapolation here, at 10 megapascals and 5 degrees Celsius, this stuff will last, this is a logarithmic scale you can see here, it'll last almost 10 to the 6 cycles. At 10,000 psi and, what's this temperature, 45 degrees, it only lasts 1,000 cycles. And at 10,000 psi and this temperature is 60 degrees, it only lasts about 12 cycles. So you can see the fatigue behavior, the fatigue life of this particular polymer is much shorter at elevated temperatures than it is at room temperatures. So although you may be a little bit unconvinced that the mechanical stress that is experienced by the polymer at room temperature is sufficient to fatigue it, these results, if they play out for polyethylene, show that at an elevated temperature, which these polyethylenes will encounter in service, there is indeed likely to be a fatigue failure, which will be quite significant. So our plans are to carry out fatigue testing of cross-linked polyethylene and tree-resistant polyethylene at elevated temperatures, and also to do fatigue testing of these polyethylenes in chemical environments that interact with polyethylene, because although we've emphasized in this talk the mechanical effect, there's no doubt going to be some chemical effect. So the failure of these materials, breaking of the chemical bonds, propagation of cracks through these materials must be affected by chemistry, even though the driving force here appears to be mechanical fatigue. And I'm going to skip over this slide, except to tell you that environmental stress cracking is the failure of a material, typically a polymer we're talking about, under a constant mechanical stress in the presence of some hostile environment. Well, and quite a bit of work has been done on environmental stress cracking of polyethylene. What's not been done is the fatigue behavior of these polyethylenes under these hostile chemical environments. So we plan to do fatigue testing in environments other than air. And this is I think this might be my final slide. This is our new cell for environmental and elevated temperature testing of these materials. So there's your sample. These are the new grips that we've built, and a little chamber around this thing. And what's not shown is a nozzle which will bring solution and spray it on this sample as its testing proceeds. That solution dribbles out the bottom here, goes through a pump which recycles it back to the nozzle. So we can expose this sample here to to a small amount of solution without that solution interfering with the mechanical testing. We've also got a means of heating the outside of this thing so we can test at elevated temperatures, and I guess we could do both. We could test at elevated temperatures for hostile environments. So my conclusions are that finite element calculations of fields, forces, and stresses, coupled with our mechanical testing, give results supporting the opinion that the static electromechanical school of thought on water trees is incorrect. The stresses that are developed electromechanically are not sufficient, we believe, to break the stuff under static conditions. But we don't have static conditions in these cables. Instead, we have fatigue conditions. And fatigue testing has shown that fatigue is a real phenomenon with this material and suggests that it will eventually fail, years, tens of years, in fatigue at stresses similar to those calculated by the finite elements. Even in air at room temperature, fatigue failure is likely to be more pronounced at higher temperature or in chemical environments encountered in service. An examination of failure under these conditions is underway. And that's my final slide. Thank you for your attention. Ask me about space charge, Steve.
Well, yeah. Okay, a couple things. First of all, when you do a thermal calculation on a cable, most of the temperature drop is in the soil. So you can't fix the outer temperature at room temperature.
But that makes things worse.
No, the normal temperature drop across the yeah, maybe if you want to look at it that way, you're right. But the normal temperature drop across the insulation would be about 12 degrees. So the outer part of the wall of the insulation of the cable is not a whole lot lower than the conductor. Okay, well, if I make that surface hotter than the room temperature, then this is going to get even hotter. Yeah. Right. No. We fix the inside. That's fixed by what you can do.
This temperature?
Yeah, that temperature is fixed because your maximum operating temperature is 90 or whatever.
No. That temperature is given. We don't have a fixed temperature here. We have a heat generation source.
Then you've got too much heat. So
one way or another.
One way or another, that temperature is only allowed to be 90 C. Period. You don't take it above that, except under emergency conditions.
Yeah, but look. These are temperature measured somewhere.
Somebody screwed up badly, okay? I mean, somebody made a big mistake.
We'll ask Lamar about that.
You don't let. I mean, look. If you take another thing, you take polyethylene. The yield stress at room temperature is about 20 megapascals. At
13, go on.
Whatever. If you go up to 100 C, the yield stress is below 1. Mm-hmm. So you know right away what's going to happen if you start pulling on it with 2.
Okay, that's true, but it's only in the vicinity of the water trees that those stresses will be experienced. Yeah. All right. So I'll come back to the point that this thing is a finite element calculation using the properties available in the literature for all the constituent materials here, imposing an I squared R on this thing. We know that the conductivity of the aluminum, for example, the I squared R calculation of the source term is quite simple. The only thing we don't know is what is the outside temperature here. And if you're telling me it's higher than the 25 degrees Celsius that I suppose, that's going to make this polyethylene hotter still.
Yes. However, you have to limit the power dissipation to keep that temperature down.
Well, okay. 90 C. I recognize that, and that means that there's a limit, obviously, on what sort of current we can pass through this thing. Right. But I think for this particular cable, it was somewhere in this vicinity, suggesting that 60 degrees is not unusual, right?
Now, the other issue, which is the space charge issue, is that the space charge limited field for polyethylene is around 250 megavolts per meter. So, at that point, also the calculation as you did it is no longer terribly valid because...
I agree entirely.
Yeah.
I took some results from the grand young man of water treeing. This is Steve Boggs' results showing the effect of the electric field on the conductivity, right? So as you go up in electric field, the effective conductivity increases.
Yeah, the red line would be more typical of polyethylene.
Either one will do fine, okay? So what does that mean? That means that where I've got a concentrated electric field here, the conductivity here will be much higher than it is out here someplace. What that does is essentially effectively elongate this ellipsoid here.
Well, at the ends, the maximum field at the ends is limited by the high carrier mobility.
Yeah.
So basically...
Yeah, the phenomena limiting the current I don't care about for the moment. I'm suggesting that what that does is give this region here a much higher conductivity than out here someplace, which has the effect of essentially elongating this region of high conductivity, and therefore it enhances the stress.
I would look at it very differently, because you can look at it quantitatively. Basically, what you're going to have is a space charge limited field there. You can calculate the space charge density, which may be a couple of thousand coulombs per cubic meter. You know what the field is because that's the space charge limited field, and therefore you have a cyclic force, which is the field times that charge density. You have a cyclic force density. Yeah. So you can actually make that quantitative fairly accurately.
I agree. This only occurred to me about 4 o'clock this morning, so I decided I'd throw it in and see how we went.
Any other questions?
Yeah, quick one about the geometry of this ellipsoid. Could it be because you know, if you look at cables, you rarely find this kind of shapes there. Could it be that it is connected to small voids, which you see with a hydrophilic region between the two voids?
So it can be say a spherical void here, a long channel, and another spherical void
right,
here.
I think that's probably more of a
We've done that calculation, and the effect is roughly the same. I mean, it's not, you know, it's not precisely the same, but it's the same order of magnitude.
Or you could even include then a whole water tree shape, and you know.
Okay, we like simple things. The virtue of this is it's axisymmetric, so it's an easy calculation to do. But we have, in fact, done some calculations of a more convoluted structure. Yeah. And, you know, the results are in about the same order of magnitude. You need something long and skinny. Yeah. And you know, the details of the shape don't match all that much.
Okay. Just one comment about the temperature. It's not in my experience. I mean, the worst performers in this kind of water tree environment are cables that are barely loaded or even not loaded at all because they're energized just from one side.
Yeah, but, you know, how do you know what happened 20 years ago?
No, these cables are tap lines. They have a few transformers that can't be overloaded. You know, there's a lot of other cables, main feeder lines, where we don't experience cable failures, more accessory failures from connection and the like. So I wouldn't put, just from experience, I wouldn't put too much emphasis on temperature.
Well, we'll find out when we fatigue these things at temperature.